Hello students, welcome to Sri Jayendra's Ring Zone classes. I am your friend and mentor for coming classes with respect to physics. This is lecture number 4 of our unit electromagnetic induction. So let's begin with today's class. In today's session we are going to discuss about the motional electromotive force. It's a motional EMF that we call as it's a motional EMF. It's a motional electromotive force. So what it is and how it works. Let's begin. So let's understood that we have a straight conductor, and this straight conductor named as a P2Q. It is moving in a uniform and time independent magnetic field. So this figure shows a rectangular conductor. It shows a conductor PQRS in which the conductor PQ is there, which is free to move, and this PQRS, it forms a closed circuit enclosing an area that changes as a PQ moves. So if it has been placed in a uniform magnetic field B, which is perpendicular to the plane of the system, and length of the R2Q, length of this R2Q is the X, and length of the R2S, this one, it's a R2S, this one, it's a length L. The magnetic flux d phi enclosed by the loop PQRS will be phi is equals to B into area, while area could be written as L into X. So this is phi that we given as in B into L into X. Since X is changing, because what happens that this is moving, and is this if this is moving, that means this segment, a segment of X, is keep on changing, and if X is changing with time, the rate of change of flux phi will induce an EMF that can be considered as E is equals to minus of d phi by dt. And while I write minus of d phi by dt, I can have it's a minus of d by dt of blx. This minus of b into l into dx by dt, it's a differentiation of time. It's a differentiation of length with respect to time. It gives me the velocity. So this is equals to blv, while dx by dt is equals to minus of v, which is the speed of the conductor that we call as in pq. This blv, it's induced EMF that is called as the motional EMF. This is do exist because of motion of a conductor. That's why it is known as the motional EMF. I hope this is clear to you. Is it clear? Is it any doubts? Is there anything? Is there no? Great. Now what would be the direction? What would be the direction of induced current? That can be obtained using Fleming's right hand rule. So let's stretch your fingers. This is thumb, this is first finger, and this is the second finger. Then if your thumb represents the direction of velocity of the conductor, first finger represents the direction of the magnetic field, and second finger will represents the direction of induced current. So this is how motional EMF behaves. This do exist due to the motion of a conductor. This is one of the approach to study this. Let's look at the another approach and another concept behind this. That let's understand that this is the magnetic field, something like this. Yes, and we have a conductor. Length of this conductor is L, and it is moving in this direction with speed v. Now we understood that if this particle, if this rod is made up of so many charges, and if this is moving, then according to the forces, according to the theory, we have one of the magnetic force which could be written as q into bracket v cross b. This is the magnetic force. Now direction of the magnetic field is inside, direction of the velocity is in the positive x direction. So direction of the force will be in this direction. This is, we can say, fm. It's a magnetic force. And this is the the magnet direction of magnetic force on the positive charges. So what happens that in this situation, in this part of the road, the positive charges starts accumulating here. So this is the position, this is the place of the positive charges. And on the negative end, the electrons would be there. You can check it out, you can check it out using the directions. Yes, so all the positive charges would be accumulated on the upper side of the road, and all the negative charges would be accumulate themselves in the lower end. So one more force that we call as an electric force will do exist on this, and this is equals to q into e, and this is acting in the negative negative y direction. So this is Fe is equals to q into e. Now let's assume that if Fm equals to Fe, these two are the same in magnitude, then we can have it's a q into bracket v cross b, that is equals to q into vector e. This q can be gone, and this e is equals to v cross b. I hope this is clear. Is it clear? Is it? Is it clear? Is it great? Now let's have a dot product on both the sides with length element. So this could be E dot dl, that could be written as V cross B dot dl. So this is E dot dl, and that would be equals to V cross B dl. E dot dl, have you remember? It's a first unit and second unit electrostatic potential and capacitance. A second unit we used to have this E is equals to minus of dv by dr, and from this we have dv is equals to E dot dr. It is the same thing, E dot dl. So this we have this, it's a E dot dl, that is equals to V cross B dot dl. I hope this is clear. Is it clear? Is it clear that E dot dl is equals to V cross B dot dl? Is it? Is it clear? Great. So if E dot dl is being represented as EMF, that we call as a motional EMF, that we denote by the E, this is equals to V cross B dot dl. This is the vector form of motional EMF, but EMF is scalar, so it is scalar. The other end answer of this V cross B, it's a vector, and it would be the dot product of this two vectors. Dot product of this two vectors would be the scalar, and it is the motional EMF. I hope this is clear. Is it clear? Okay. If I want to write the scalar form, then I can write like this, it's a E is equals to B into V into L, but with certain conditions. We are going to discuss those conditions, but first focus on this. When and when write E is equals to B into V into L, this B is the magnetic field of the region. It's a magnetic field of the region. When we talk about the V, it's a velocity of conductor, and when I say it's an L, it's an L, let me write this. So L is the effective length of the conductor. Now while I say effective length of the conductor, even I have used this word when we used to study moving charges and magnetism. We have the force acting on the current carrying conductor, that was F is equals to BIL sin theta. Yes, even at that time L was taken as the effective length of the conductor. It is line joining, it is the line joining initial and final point of the conductor. So while I say effective length, I mean it is the line joining the initial and final point of the conductor. So this motional EMF could be written as E is equals to B into V into L. That's it. It is as simple as that. I hope it is clear. But again, certain conditions applied. Now let's look what are the conditions I'm talking about and how they will act on my situations. Let's have a look. So when I say that E is equals to BVL, and if you look at this my relation very carefully, it is something like this. It's a V cross B dot DL. While I write V cross B dot DL, while I write V cross B DL, I understand that if any of the two parameters are parallel to each other, are parallel to each other, then motional EMF, motional EMF will be 0. I hope this is clear. Yes, this, it's a V cross B that we call as in VB sine theta. Let's say if V is parallel to the B, this will be 0. So first thing that has been clear. One more thing, let's say V cross B, V cross B will give me let's suppose certain vector that we can call as the C. Let's suppose C would be the answer of V cross B. Now let's suppose B and DL is parallel, then it means C and DL must be perpendicular to each other, and any vector that perform a dot product with another vector having an angle of 90 degree will convert to 0. So I hope this is clear. That please keep this in mind, please keep this in mind every time if any of this two parameters, we have three parameters, it's a V, it's a B, and it's a DL. We have three vectors. If within this three vectors, if any of these two are parallel to each other, that means its motional EMF will be 0 for sure. I hope this is clear. Is it clear? Is it clear? Now next is the how to determine direction, or I should say polarity of EMF. How to determine the polarity of EMF, or I should say cell, because it behaves like a battery. Use your right hand. Then fingers first points out towards the direction of motion, and then curl them towards the direction of magnetic field. That use your right hand, your fingers first point out towards the direction of the motion, and curl them towards the direction of magnetic field. Then thumb will represent the positive terminal of the cell, and once you have the positive terminal of the cell, you can easily have the negative terminals of the cell too. I hope this is clear. Is it clear? Is it? Let's check it out once. Let's suppose this is magnetic field, and this is road, and it is moving in this direction. Let's say from here to here the length is L, this magnetic field is P. So it's an E is equals to B into L into V. That I understand. Yes, magnetic field is inside, length vector is in the J cap, while the velocity vector is in the I cap. Now what about the direction? So use your right hand. Show me your right hand. Show me. Yes, use your right hand. First first stretch your fingers in the direction of motion of the conductor, so it should be in y direction. And now your fingers should point it down. Now your finger should point it down. If it has been pointed down, then you will understand that this end, the upper end, let's call it as a C, this end as a D, then the upper end C will be on the side of a thumb. So when C is on the side of a thumb, it will look like this. This is the motional EMF, and this battery will behave as the value of the E is equals to BBL. I hope this is clear. Is it clear? Is it clear? Are you sure? Are you sure? Any doubts? Is there anything? Is there any doubts? Is there anything? No? Let's have a look certain questions and we will be back to the numericals. It says that when a conductor carrying current is free to move in a magnetic field, the direction in which current will move, is given by S, that has been given by the Fleming's left hand rule. And next the direction of induced EMF, they said induced EMF, the direction of induced EMF is determined by, yes, it has been determined by Fleming's right hand rule. I hope this is clear. Is it clear? So now are you ready for the question answers? Are you ready? Are you sure? Can we do this? Can we be ready with your pen and paper? And let's do it with me. Let's start it. The question says that find out motional EMF the situation is something like this. A magnetic field is there and conductor has been placed in this magnetic field. This is the center and this is the radius R. This is moving in the upward direction. Yes, so this is P, this is Q. So how will I calculate? So first what I need to understand is write down the master formula. The master formula say it's a B into V into L. Now when I say this is E is equals to B into V into L, when I say B into V into L, my L is the effective length of the conductor. When I say effective length of the conductor, that means this is the line joining initial point and final point of the conductor. So this is 2R. So I should write this as a B into V into 2R. This is the motional EMF. I hope this is clear. Is it clear? Great. Now next we need to understand that which terminal will behave as the positive terminal and which terminal will behave as the negative terminal of the battery. So how will I do this? That first you should use your right hand such that your fingers will point towards the velocity of the conductor. That means it is in the J cap in this situation. So if you use your right hand like this, then bend it in the direction of the magnetic field. So thumb will be there. It is something like this. This terminal will behave as a positive terminal and this will behave as a negative terminal. So it is something like this. This is positive, this is negative. So this is B, V, 2R. This is the motional EMF of the conductor. This is E is equals to B into V into 2R. I hope this is clear. Is it clear? Is it is it clear? Are you sure? Are you? Great. So ready for the next question? Are you ready? Let's have a look. Suppose a magnetic field has been arranged like this, and a conductor is there, something like this. Yes, and this conductor is moving in this direction with constant velocity v. Let's give them a name. Magnetic field is the B. This is P, Q, R, S. This length is L. This length is L. This length is L. Question says that find out motional EMF of given situation. So how will you do this? If you observe the motion of PQ, let's look. P2Q, its length element is in this direction, it's a dl. Its velocity again in this direction. So for this dl and v are parallel to each other, and when any two vectors within this three vectors are parallel to each other, if any two vectors within this three vectors are parallel to each other, that means motional EMF due to conductor PQ is 0. Now let's talk about the R and S terminal. Let's talk about the R and S terminal. That even R and S terminal, the length vector is dl, the velocity vector again in this direction. Theta is 0, and when theta is 0, the ERS will be equals to 0. Let's talk about the Q to R. It's a EQR. Its length element is in this direction, its motion is in this direction, and magnetic field is inside, so everything is perpendicular to each other. So we can write it's a B into V into L. Now let's talk about that, which terminal will become positive and which terminal will become negative. So when I say this, when I look at this, use your right hand, stretch your finger towards the point where my conductor is moving. In this case it is moving in the positive x direction. So stretch your hand, and now curl your fingers inside the plane. So you will find that this is positive, this is negative. It is something like this. I hope this is clear. This is BVL. Q would be at the positive terminal and R would be at the negative terminal. This is BVL. I hope this is clear. Is it clear? Is it clear? Any doubts? Is there anything? No? Great. Let's work for the next question. It says that find out motional EMF. So now in this case the situation is something like this. Let's say magnetic field is there, and within this magnetic field a conductor is kept. This is the reference line, and this conductor is moving in this direction. This is the theta. So let's understood that this is the P and this is the Q end, and this is the L is the length of the conductor. So in this situation what I need to do is that this velocity v makes an angle theta with vertical. So what I need to do, I need to find out their components. One of the component will be this, and this would be the v cos theta. The other component would be this is v sin theta. Yes, and now I understand that v cos theta, magnetic field B, and length element L, all these three are perpendicular to each other. So the motional EMF could be written as B into L into V cos theta. I hope this is clear. Now one more thing, as you can see that the velocity vector is moving in the plus y direction, the magnetic field is inside the plane of the paper, then thumb will represent the direction of the positive terminal. So this would look like this, something like this. It's a P and it's a Q. I hope this is clear. Is it clear? Is it clear? Any doubts, any issue? Is there anything? Do you understand each thing, everything clearly? Are you sure? Are you? Great. So let me write down one more question. We have an ample amount of space over here. So the thing is something like this. A magnetic field is there, and the magnetic field has been arranged in this. This is the B. So in this situation, it is something like this, that this is the conductor, and let's suppose this is theta, even this is theta, and this conductor, let's suppose this is the length L1, this is the length L2, and this is moving in this direction with speed v. So when I say this, what I understand is that this is making an angle theta. So I would look for the perpendicular component. If this one is L1, this should be the L1 cos theta. This would be the L2 cos theta. So this one would be the L1 sin theta. This one would be the L2 sin theta. So this is L1 sin theta, L2 sin theta. Now motional EMF E would be equals to B into V into effective length. The effective length will be equals to L1 sin theta plus L2 sin theta. I hope this is clear. Now which one is the positive terminal, which one is the negative terminal? So it will behave look like this. Yes, this is the positive terminal and this is the negative terminal of the battery. Do you understand this? Have you understand this? Anything which is not to be understood? Are you serious? Everything is clear? Is it clear? Great. So ready for the next question? Keep doing this, this will help us to get it done in fractions of seconds, and that is our requirement. Let's say that conductor is something like this. Yes, a conductor is looking like something like this. This is the length L, even this is the length L, and this angle is 60 degree, and let's say this is moving in this direction with speed v. So what happened? What would be the situation? So the situation would be that this would be the, let's call this end as a P, this end as a Q, and this end as a R. Then motional EMF E would be equals to B into V into L effective. When I say this motional EMF E is equals to B into V into L effective, this would be the point where road has started, this is the end where road has ended. So this is the effective length. You can understand this is L, this is L, so this must be L. Yes, it's an equilateral triangle. So this is equals to B into V into L. Now which terminal would be at the positive end and which terminal would be at the negative end? Use your right hand, but use it carefully, because here the velocity is in the negative y direction. Generally it is in positive y direction. In this situation it is in negative y direction. So when you hold your hand such that its EMF is in the negative y direction, then you will understand that this is the situation where this and R would be at the higher potential while the P would be at the lower potential. this will something like this. This is R and this is P. I hope this is clear. Is it clear? Is it? Are you serious? Any doubts up till now? Is there anything? Is there anything? Are you sure? Are you sure? Do you understand this? Do you understand this? Any doubts? Any doubt? Is there anything? Is there? Is there anything? No? Great. So shall we move to the next situations? Let's have a look. Suppose the question is something like this. This is the magnetic field, and in this magnetic field a conductor is there, and this conductor is hinged over this at the end. This conductor is having a length L. This conductor is having a length L, and this conductor is going to rotate. This conductor is going to rotate in the plane, something like this. What do you want? You want to find out motional EMF. This is the requirement. You need to find out the motional EMF. How will you do it? Please think and let me know. How can we do this? What is to be done? What can be done to this? So what I understand is that first you need to consider a smaller amount of segment, and the thickness of the segment is dx, and it is, let's say, at the x distance, and write down the motional EMF for this element only. So while I write this, it's a dE that is equals to b omega. It's a b into omega into x dx. I hope this is clear. Yes, we are writing the same thing. Do you know v is equals to r omega? Do you know this? Yes, our master formula, it's a b into v into l. So as it is going to rotate in this direction, x will behave as a radius. So v is equals to r omega. It's an x into omega, and the length, only this segment is going to rotate. When I write dE, this L has been replaced by the dx. Do you understand this? Yes. So let's just integrate this. This is, when this is integrated, this is motional EMF E. This is motional EMF E, and this is to be integrated from 0 to L. Yes, because this end is the 0 and this end will be the L. So this is b into omega into integration of x dx, starting from 0 to the ending at L. While doing this, it's a b into omega into integration of x dx. This is x square by 2, starting from 0 ending at L. So that should be written as, it's a b into omega into L square by 2. This is the motional EMF. I hope this is clear. Is it clear? Is it clear? Please do remember this. This is very important formula. This motional EMF E would be equals to, for a rod, it's a b into omega into L square by 2. I hope this is clear. Is it clear? Is it? Are you sure? Great. Now, what would be the direction of the battery? What would be the direction of the battery? So what you are supposed to do, the same thing. You are supposed to do the same thing. When you consider your direction of motion, you, at that instant you need to consider the direction motion in the upward direction. And now bend your fingers in the direction. Then you will find that your thumb will point towards this O. That means this battery will be something like this. This is at the higher potential and this is at the lower potential. I hope this is clear. Is it clear? Any doubts? Any doubts, any concern over here? Is there anything? Anything? No? Great. Now let's work for this kind of questions only. So let's suppose the situation is something like this. Do you enjoy this? Do you? Great. Now let's suppose understood that this is the road of length 2L. This road is of length 2L, and this has been hinged. This has been hinged from the middle one, and this is going to rotate it something like this. Yes, so this end would be in this direction, and this end would be in this direction. So the question is find motional EMF between two ends of conductor. So we need to find out the motional EMF between two ends of the conductor. How will I do this? What could be done? What could be done? One of the easiest approach, what I understand is that let's just divide this. Let's just divide this into two segments. Then you will find that your first segment, let's call this as a first segment. This is first segment. Magnetic field is inside, and this is going to move in this direction. So this would be, it's a b omega l square by 2. We have just derived this. Yes, we have just derived this, and its direction will be something like this. I hope this is clear. Is it clear? Is it clear? Great. Now let's consider the second segment. Second segment, it is something like this, and it has been hinged over here. This has been hinged over here. This has been hinged over here, so it is moving in this direction. So if you use your right hand, and consider the direction of motion and then direction of the magnetic field, then you will find that your thumb will points in this direction. I hope this is clear. Again, the motional EMF magnitude wise, it will be having the same value. It's a b omega l square by 2. I hope this is clear. So if I give them a name, this end is p, this end is q, this end, it's an r. It will look like that from p to q. From p to q, it is something like this. This is p, this is q, and from q to r, it is something like this. So this is E1, this is E2. So when I write E1 to E2, have you remember the combination of the cells? Do you remember this? I can write it's an E net, that is equals to E2 minus E1. Let's say this E2, it's a b omega l square by 2. This E1, it's a b omega l square by 2, and thus E net would be equals to 0. That's it. What was your answer? What was your answer? Was it same? Was it same? Are you sure? Are you sure? Great. Do you understand this? Do you understand this? Are you sure? Are you sure? Great. So now let's look at this. We have derived this one, and I want that you guys do remember this. This is the master formula. Why this is the master formula? Let me introduce you to the very new thing. We have this E is equals to b omega integration of x dx from 0 to L. I introduce it from initial to final. Yes, so now this can work for any of the root. Let's say it has been hinged at here, and let's suppose this total length is L. This is 3L by 4, and this is L by 4. So I can write it's a 0 to 3L by 4 and 0 to L by 4. This one as a first, this one as a second, and rest among the thing you can do. I hope this is clear. So this is the master formula that everyone should remember. because based on this formula only we can do the other task. I hope this is clear. Is it clear? Is it clear? Are you sure? Do you understand this? Do you? Do you understand this completely? Yes? No? Yes? Great. So let's do one of the question based on this, that magnetic field is arranged like this, and the road is being arranged something like this. This is the position where it has been held, and let's take that numerical only. It's a 3L by 4, and this is L by 4. So what do you need to do? Let's call it that this is P, this is Q, this is R. What do you need to find out? You need to find out that question says that find motional EMF, find motional EMF between two ends of the conductor. This is the requirement. So what you need to do is mark it with the road 1 and road 2. This is first, this is second. So for first it is something like this. This length is 3L by 4. This E is equals to B omega into L square by 2. This is master formula. It's a 1 by 2 into B into omega into L square. It's a 3L by 4 whole square. So this is 9L square by 16. This is 9 by 32 B omega L square. And as this is moving in this direction, it will something like this. So this is from Q to R. This is 9 by 32 B omega L square. Now let's work for the P to Q. So the P to Q segment will look like this. It has been hinged over here, and this segment can work for P, this segment can work for Q, and it is moving in this direction, and this is just the L by 4. So this EMF is equals to B omega L square by 2. It's a 1 by 2 into B into omega into, this is L square by 16. So this is equals to B omega L square by 32. When I write this, I can have, it's something like this, that this terminal is positive and this one is negative. So it would be something like this. It's P, this is Q. I hope this is clear. So net E net would be equals to 9 by 32 B omega L square minus of 1 by 32 B omega L square. It's a 9 minus 1. This is 8 by 32 B omega L square. This is 8 by 32, 1 by 4. It's a 1 by 4 into B omega L square. That's it. This is E net. I hope this is clear. Does it clear? So, do you understand the complete concept? Do you understand the complete concept? Are you sure? Are you sure? Are you sure? Can you do this? Can it be done? Can it be? Great. Ready for the next question? Let's have a look. You are doing pretty good, but make it quick. Let's suppose a magnetic field is arranged such like this, and when magnetic field is arranged such like this is the circle, and let's suppose this is circular wheel. These are the spokes of this wheel. Yes, so this all have been hinged over here. This is the location where they have been hinged at the center, and this wheel is going to rotate in this direction. I hope this is clear. So if I understand that each one is having a length L, each spoke having a length of L, they said that find EMF induced across its ends. This is the requirement. How will you do this? How will you? How could you do this? What can be done for this? What do you think? What I understand is, let's consider each segment one by one, and you will find something very interesting in it. That let's suppose this is the first road. Use this. This is a first road. Yes, as this road is moving in this direction, so it's an EMF, it's a 1 by 2 b omega L square. Same way, let's consider this road. Yes, it is moving in this direction, it is moving in this direction. Same way, EMF of this, it's a 1 by 2 b omega L square. Same way, let's take this road, and this is moving in this direction. As this is moving in this direction, it's EMF, it's again half b omega L square. Let's consider this road, even this is moving in this direction. Again, this is E is equals to half b omega L square. I hope this is clear. Is it clear? Now start making according to the terminals of the cell. If I work for this, this will be the positive and this will be the negative. If I work for this will be the positive and this will negative. If I work for this, it is positive, it is negative. If I work for this, it is positive, it is negative. So if you look at this very carefully, that this end and this end, this end and this end, this ends, this end, if I connect all these ends, it is something like this. Yes, this all are the parallel combination, having same potential difference, something like this. And it is independent of the number of the spokes. Everything E, so the E net would be equals to half b omega L square. That's it. This is independent of number of spokes. This is very interesting, that in this situation we have drawn 1 2 3 4 5 6 7 and 8. We have 8 spokes, but even though it was the case of 24 spokes, the answer would be half b omega L square. Even though it was the question of 108 spokes, the answer would be the 1 by 2 b omega L square. So one thing that came in my mind is that, let's say this is a circular disc and a magnetic field have been arranged in this. This is the center, and this circular disc is moving like this. It is having a radius of r. So if this is the case, and they ask me that what is the find out motional EMF. So how will I do this? What I need to do to perform this? How can I? What should I do? What is there in your mind? How will you do this? How will you do this? So what I understand is that consider this disk as a summation of infinite number of spokes. When I consider this disk as a summation of infinite number of spokes, what I understand is this is E is equals to 1 by 2 into B into omega into L square. In this case L, that is the length of the spoke, will be replaced by the radius of the ring. It's a 1 by 2 into B into omega into R square. This is the motional EMF of the ring when it is rotating like this. I hope this is clear. Is it clear? Is it? Are you sure? Are you sure? Can you do this? Can you? Can it be done? Are you sure? Are you? Great. So now do you understand this? Do you understand the complete situation and complete motion? This is the motional EMF of a conductor. Now, let's have certain very good conceptual questions. The question says that, let me draw the diagram first. Let's say this two circular conducting rings are there, and this ring is having a radius of 2r, while this ring is having a radius of r. This is moving in this direction with speed v. This is moving in this direction with speed 2v. So what I need to find out, I want to find out that find potential difference. Find potential difference between the highest point, between the highest points of these two rings. How will you do this? What can be done? What do you think? The magnetic field in this region is inside the plane of the conductor, something like this. So what I understand is I should consider both the rings as an individual one, and I need to write down their motional EMF. So if I write down this ring as a cell, what I understand is, use your right hand. Have you used it? Yes, great. Now use your right hand and write down the relation that this upper end would be the positive, so it is something like this. This is positive, this is negative, and something like this. So this could be written as E is equals to B into V into L. Length would be equals to, from this to this is 4r, so this is equals to BV 4r. Now let's work for the second ring. This is moving in this direction. Use your right hand, but use it correctly, because the direction of motion is negative x direction. If you use it correctly, then this will represent it as, this is negative and this is the positive. I hope this is clear. Is it clear? Yes. So this could be written as BV into this length. It's a length from here to here. It's a 2r. Let's connect this because they have been connected. So this is the first point, this is the second point. I am looking for the potential difference between these 2 points. As this two are connected in series, but this is moving with 2v, so this is equals to v dash. This is b into 2v into 2r. This will be 4bvr. Yes, as these two are connected in series, I can write E net, that v is equals to, let's call this E1, call this as a E2. This is equals to E1 plus E2. Both are 4bvr plus 4 BVR. This will be equals to 8 BVR. That's it. This is E net. You did it. Great job. I hope this is clear. Is it clear? Is it? Do you understand this? Have you? Have you understand this? Are you sure? Are you sure? Are you sure? Great. So now ready for the next question? Are you ready? Let's look at this. We have an infinite length of conductor and current is flowing through it. Yes, it is an infinite length of conductor, and we have one of the conductor which is placed over here. The length of this conductor is A, and this conductor is at a distance of B from this wire. Yes, and this road is moving in the vertically upward direction with a speed of V. So what I need to find out is that find out induced EMF in total length of conductor. How will you do this? They said find out the induced EMF in the total length of the conductor. How can you do this? So one thing is sure, that what I understand is that let's understood that E would be equals to B into V into length of the conductor. But the problem is this B, because B, it's a mu naught I by 2 pi r, while r is the distance of each end will be a different one. For this will be different, for this will be different. So what I, or how should I do this? So in this kind of situation, I should always take an help from, I should always take a help from the integration. This is a smaller segment which is at distance x, and the thickness of this is dx. So first let's find out the EMF. It's a E that should be is equals to integration of d into E. That could be written as it's a B into V into dx. This is just the B into V into dx. Now one more question is how to integrate this and what is to be limit of this. So this road starts from here and it is ended up here. This is at distance B, so this end will be at distance of, from this it's a B plus A. So this is to be integrated from B to B plus A. I hope this is clear. While doing this, let's replace the B is equals to mu naught I by 2 pi r. So this could be written as mu naught into I divided by 2 pi x into V into dx, starting from B to the ends at the B plus A. So do it carefully. Let's have a look. We have this relation E is equals to, let's write down all those which have been not to be integrated. It's a mu naught I into V divided by 2 pi. So integration of dx by x starting from B to the A plus B. This is equals to mu naught IV divided by 2 pi integration of dx by x. It's an ln x. So this is from B to A plus B. This is equals to mu naught into IV divided by 2 pi. This is equals to ln A plus B minus of ln of B. And while doing this, this EMF E is equals to mu naught IV by 2 pi to bracket ln A plus B by B. This would be the answer. A very good question. I hope you understand this. Do you understand this? Do you understand this? Are you sure? Ready to have one more question like this, with a little variation? Are you ready? Let's have a look. Our very conceptual questions. Let's suppose a same thing is there, that this is a wire or infinite length conductor, and this is a square loop. This is a square loop, and the dimensions of the square loop is a by a, and it is moving in this direction with speed v. The center of this two wire, this, they have been separated by a distance of r. They have been separated by a distance of r. They want that, find out induced emf in the loop. But they have given one very important condition, that r is much greater than a. Yes, this is given. So what does it make a difference for us? When this distance is much larger to this, you can consider this square frame as a point object. And when you can write this as a point object, your magnetic field on total loop will be the equal. So the problem arise in this case was, this was not point object, so magnetic field at here and magnetic field at here would be the different one. It is not the case in the current numerical. So what I can write, it's a b would be equals to mu naught I divided by 2 pi r, and the, if b is none, I can have flux, it's a b dot a, that could be written as mu naught I by 2 pi r multiplied by a. A is the a square. We are talking about the square loop. And now we have the we have the phi. We need to find out the emf. How will I do this? What could be done? So it's an e that should be is equals to minus of d phi by dt. This d phi by dt, that could be written as, this is equals to minus of d by dt of, this is equals to mu naught I by 2 pi r into a square. So this could be written as, it's a mu naught I a square divided by 2 pi into this is d by dt of r to the power minus of 1. This is the situation, this is the emf. So if I solve this, this is minus, yes. So this emf e could be written as, it is minus of mu naught I a square divided by 2 pi into d by dt of r to the power minus 1, it's a minus of 1, into r to the power minus of 2, multiplied by dr by dt. So this minus and this minus will be the positive one. This is mu naught I a square divided by 2 pi into 1 by r square into dr by dt. This dr by dt could be written as v. So this motional emf could be written as mu naught I a square into v divided by 2 pi r square volt. I hope this is clear. Have you got this? Do you find this interesting? Yes, I love this. Do you understand this, each and every aspect clearly? Do you have any doubts? Is there anything? Do you understand this completely? Great. So let's just wind it up this session over here. This is all about the motional emf. Please have a practice based on this. Basically we have up till now we have covered things, that is, first is the magnetic flux, second is the emf, and to find out the magnitude of emf we have taken a help of the we have taken a help of the Faraday's law. Then we have done the direction of the induced EMF using the Lenz law, and now it's a motional EMF. So this all are very rich concepts, and to have a command over it you need to practice a lot. But that is for sure that once you make a practice, this will be delivered to your subconscious mind, so it will be with you until your exams over. So please, it is better to make a lot of practice so that this can be done even on the day of an examination. I hope this is clear to you. Thank you, have a good day, take care, bye bye.